So now you have that packet. It's a great thing to work on. It hones everything. Like it's just a great thing to hone your skills. What did I say about answers? I've got them on my desk. Okay. All right, I'm moving on. So the mean value theorem, I just wrote it. I'm going to refer to it in a moment. All right. The mean value theorem is up here for reference. I know you know what it says. I'll refer to it in a moment. Here, I'm switching gears. Let's do this. Notice something here. I am just going to call this function f prime of x. All right? Just calling that function f prime of x. And all I'm going to do is now do this. Okay? And we have been talking about the definite integral from a to b of this function. And the thing is, here's why it doesn't really matter what this function is called, right? I mean, I'm calling this function f prime, I can call it g. It's just a function that happens to be called f prime because the derivation is going to work this way nicely. After I do this, I'm really curious to see how you four kind of unveiled this moment last year. I'm really curious to hear about it. What we've talked about up until now is doing something like this, looking at rectangular subintervals, okay? Looking at rectangular subintervals. For ease, I just have been talking about a right endpoint Riemann sum, which means that I've been looking at the right endpoint, which means something like this, okay? Something like this. I'm going to arbitrarily just kind of focus on one of them right here. All right, nothing new, nothing new. I'm going to do this. This here has an x coordinate of a. Oliver, yes?
In this case, would it be an underestimate?
This would be, well, that would be, because the concavity, like eyeballing it, it'd probably be under because there's more places where the rectangle is below, right? That's a good question, all right? Look what I'm doing here. All I'm doing is writing out like this x coordinate is a, I'm calling this x sub 1, I'm calling this x sub 2, x sub 3, okay? So this is going to be x sub 4, okay, so on and so forth. Now, here's the thing. What's interesting is that the way I've numbered this, 1, 2, 3, 4, the fourth rectangle, so this is the fourth rectangle, right? Okay, this is the fourth. I'm going to talk about that in a minute. This is the fourth rectangle. Okay. And we've been talking about, all I'm going to do here is, I'm going to do a whole bunch of stuff here. I'm going to do this. Area of all the rectangles is going to equal, I'm just going to do this, x sub 1 minus a times f of x sub 1 plus x sub 2 minus x sub 1 times f of x sub 2. What am I doing right now? I'm just writing out talk. Well, no, don't say things you don't know what they mean.
What do you mean?
Or because they're all just what? Area of rectangle 1, width times height. Area of rectangle 2, width times height. Area of rectangle 3, width times height. At the very, very, very end, yes, Jabril?
Wait, are these are not rectangles?
They are.
Okay.
They are. Okay, but yeah, so you're wondering like why am I writing them all out? I just am. It's gonna work out nicely for me in a little while.
Okay.
Oh, I just caught a righto. Because I called this function f prime, this should be the f prime of x of 1, right? Because it's the function, and this here happens to be the function is f prime. So it's the function evaluated at the right endpoint. Okay. Now, if n, now let's just be careful, if n is the number of rectangles, just be careful here. So the first rectangle, right, the right endpoint is x sub 1, okay? So at b, this x coordinate right there, I could call it x sub n, okay? Which means then this is x sub n minus 1. Let me repeat that one more time. So because I numbered my x coordinates this way, if n is the number of rectangles, I'm observing the pattern. X sub 1 is the right endpoint of the first rectangle. X sub 2 is the right endpoint of the second rectangle. Because I numbered it this way, that means B I could also call the right endpoint of my nth rectangle, which is then just x sub n. Fair? That means x sub n minus 1 is over here, which means at the very last, my very last rectangle is going to be B minus x sub n minus 1 times f prime of what? F prime of B. Everyone okay? All right. And obviously, area of all rectangles is this. And we know too that because all I've written here is these little demarcations, this distance, maybe it's 1, maybe it's a half, maybe it's 0.1, maybe it's 0.000001. The point is though, the smaller this width, the greater the number of rectangles, correct? The greater the number of rectangles, the better I approximate the actual area. Agreed? As that number approaches infinity, I actually get the value of the integral. Everyone good? All right, come with me over here. This was our mean value theorem. Okay? So one of the most beautiful proofs in all of math, just fantastic, beautiful proof. This mean value theorem says, slope of a secant line must equal the slope of the tangent line at some point x, where x is between like the endpoints of the secant line, right? That's the mean value theorem. All I'm going to do with this is multiply over here. So I get f of c minus f of d equals f prime of x at some value between c and d times c minus d. Everyone okay? All right, and I'm going to have you just look at this for a second. Before I do the step that is magical, I want you to just look at this step for a second. Okay, this is all old news. This compared to this. Okay, now, let's step back for a second. Something very interesting happens. So just look at, this is just the mean value theorem, right? And here in the mean value theorem, right, this is saying this input here is some x value between c and d, all right? Here, this x value is an x value between a and x1. You understand what I'm saying? One more time. Back here. This x star value, and I purposely used different variables so you wouldn't say like, is c there, c and no. This x value, according to the mean value theorem, this x value has to be a value between c and d.
Yeah.
If you look over here, this, by definition, x1 is right here. x1 is between a and x1.
Oh,
Which means, substitute, this equals this.
So you can do like,
That means this equals f of x1 minus f of a. Notice how I drop the derivative. Because this is f prime, this is f. Okay?
wait, so technically it's not the same because it's on the right hand side of that one it's trying to get f of the x plus 1. And over there it's saying f prime of that one.
What's not the same?
Because it
F
would that
prime here.
would be minus f b.
No. Over here. See we're here? F prime at some x value. Yeah, everyone okay? Nancy?
And this last say any x will be right in this equation. It's like at that point where here, your argument is, but here we see that x1 is always at the end of the interval. Correct? Okay. So the rectangle's height, we've just done the right endpoint. But that endpoint could be the left endpoint, it could be the middle, it could be anywhere. Okay? Continue. Are you ready? This is just up here. Plus, that's the plus sign. Okay? Using this right here as the mean value theorem, this is identical to f of x2 minus f of x1
Oh yeah.
plus
F
f of x3 minus f of x2 plus a whole bunch of stuff in between, but at the end of the day, this is going to be what over here? F of b minus f of x. All right, step back. What cancels? Everything except f of a and f of b. Cancels. Boom, 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 boom. Everything except f of a and f of b. We get f of a minus, negative f of a, my bad. Negative a plus f of b. I'm just going to rewrite this so it looks better. This is the same thing as f of b minus f of a. Pause for effect. Hold on.
Silence in respect of the moment. Nicole?
What does the f of x to that like n-1? What does that cancel with?
Like the term before it. As in looking all out.
Okay,
right?
so just some generic. Okay.
Okay?
Okay.
What this is telling you is this. By the way, this, the area of all the rectangles, as that distance becomes like smaller and smaller, this is just the definite integral from a to b. Oh, what's the thing we're taking there? What's the function we're finding the area under? F prime of x dx. Why is f prime? Because I called it f prime. So let me say this a couple of times. We're going to write it. We're going to practice it. And we're going to pause for effect. Is everyone at a point where they can listen fully? This just says the net signed area bounded by some function from a to b is just the antiderivative of that function evaluated at the upper limit minus the antiderivative of the integrand evaluated at the lower limit.
Oh, oh my god.
Oh, wait, that makes it so much easier.
Yes!
Are you kidding?
Yeah, he does!
Oh my god. All you have to do is take the oh my god.
I can see you. Just the antiderivative. I'll show you.
So you just take the antiderivative and evaluate. Oh my god.
Like, here's the thing. Yeah. They're like, okay, wait, doesn't this blow your mind up?
Yeah.
Wait, so how did you learn last year? Next year, I want you to listen to this. Listen to without fighting over the Boston Creek. Please share. How did you learn this last year?
We were told that.
That's true.
Yeah, it was just,
Okay, it was just right on. Those of you moving on, you can, like, if you are only told the math works because it does, and you don't know where it came from, you're so limited in what you can do with it. Like, you gotta know where it came from. Isn't this amazing though?
Yeah. Missy M.
So now, for example, are you ready? So, Arjun, shut it now, please.
Missy M, this is glitching out. It's still recording and the stuff's still there, but
It's fine. It's fine. Let's go. Are you
Okay.
ready? Here we go. The definite integral from 0 to pi over 2 of cos x dx equals. Okay, now here's how we write this. We now know the definite integral of this function is the antideriv evaluated at pi over 2 minus the antideriv evaluated at 0. It's important you know how to write this out. Here's how you write this. This equals is how you write this. What is the antideriv of cos x? Sine x. And then you write this, or this is just new notation. You do this bracket. Whoa. Okay, well watch. 0 to pi over 2. This means, look up here, this means now sine of pi over 2 minus sine of 0. Okay? That's what this means. That is what this means. This is new notation. Now you know. Megan, yes.
Leah, what is it just to draw a line? Do you want us to draw a line?
A line's fine. A line's fine. That's fine. Either one's fine.
That middle step,
Um,
So you always write it out.
Yeah, well, here's the risk you run. Like, the risk you run is just not getting partial credit, right? So, yeah, I mean, you just want to be careful, all right? So now comes the practice piece. First of all, what's this equal? 1. 1, okay. Let's do this one. Let's do this one. Ready?
This is when we were dying.
Oh!
It's a joke to me.
Okay, chop chop.
Oh.
So Jason, do you see how it doesn't matter what Jason? Do you see how it doesn't matter what this is called? Whether it's f prime or f, it's just the antiderivative. Okay, like it doesn't matter what you want. It could be anything. It could be anything. All right.
Oh, it's just a copy.
Oh, it's back. All right.
Okay. What's the antiderivative of e to the x minus 1? Minus x evaluated from 1 to e squared. This is just plugging in correctly. I wish I had, like, this is a big marker moment. I call these when I this is a big marker moment. Big marker moments are things that should go on the board and never get erased, ever.
Oh my God.
Big marker!
Is this like when you drew the baby in that room?
How did you know?
We were in that room and then we saw that graph in the corner. We were like, that's oh, in the corner of the room. Yeah.
Oh, sorry. Big marker. This is the fundamental theorem T of calculus. Part 1. Big marker moment. These. Oh, wow. Fun. Theorem. I have had this marker for 23 years. I pull one out once a year. Not every day is a big marker day. It's not like we don't take this lightly, okay? Oh no, it's a Sharpie. I'm just kidding. That was so funny. Fundamental theorem of calculus is documented. Why are you not writing this down?
I'm documenting.
The definite integral.
Write it, people.
I already wrote it.
Yeah, I wrote it. Biggest marker I've ever seen. It's just like
What? What's that? F of B minus F of A. Now, this isn't flow. It's the FTOC part 1. Part 1.
Part two.
Oh, just wait.
Because we don't have to do the whole series summary.
Okay, Gary just said, what's the big deal?
Gary, do you
What's
want to
your
do
response,
that
Gary?
rewind sum every single time? Like that. Yes, Gary. Gary,
Would you rather
Get out.
I'd rather draw cosine x and then draw like.
set up the Riemann sum every single time.
I understand the sense that it makes it easier. I don't understand like the motion why.
Just wait.
Because what if you have like an equation that's like 4 to the, I don't know.
What if it's like 4
complicated and you have.
Yeah, what if it's like 4 to the 7x cubed minus 3x
Minus 3
to the 4?
Yeah.
It's hard to draw. Yeah. You can't draw that. So I'm trying to find it. It's because there's a lot of applications of
So this is not,
like what is
so I need to bring in Aaron for a second. Let the mayhem subside for a second. Jason just asked a really good question. He said, when you get, where you put your point to here to here? To here? Okay. Well, here's the thing. The definite, so he just asked a question, what about the issue of the family of antiderivatives? So Jason, a family of antiderivatives is described by an indefinite integral. An indefinite integral without the limits of integration. A definite integral is equal to a number, and that number is just the net signed area bounded by this curve. So that's a very good question. But the issue of the family of antiderivatives, that's indefinite integral. Okay, think about it. Just think about it. Think about it. FTOC part 1. Everyone knows what FTOC means. If you go to a party, if you say the fundamental theorem of calculus, they will think that you're not using LOL. Don't do that. Say FTOC part 1. Like it's just like, oh, please don't know that. Walk away. Stop. Goodbye.
Thank you, Miss Adams.
Thank you.
That's because this way you're showing, I know what the antiderivative is. Point. Then you're evaluating.
Oh yeah, very nice. Yeah.
And like, oh, this step would sub it in.
Yeah.
Yeah, it gets a little bit.
Why?
What's your
Right, like,
do?
Sam. Whatever light is called.
I'll put it, I'll print it and I'll say, Nicole, I put it down, you come grab it from my desk.
Okay.
Like when we were doing like limits and stuff, we did the long way, and they found like Elohim, which is like the big daddy or whatever.
Right.
This is like the granddaddy of like.
Oh, I don't know, let's like.
Hello. Okay, well.
Jasmine, 1 minute. Why do you give Jasmine 1 minute?
I have no clue.
Okay.
So you have like,
I do have many moments of algebra.
I'm just confused about like, so I'm not exactly certain how the equivalency between this and this is drawn.
Oh, okay. Do you have class right now or no?
No.
Okay, let's go out. Let's go because there's a class in the
Okay.
Okay, yeah. So think about it a little bit. Okay.
So this e to the e squared minus e squared minus e minus 1.
Yes, minus the quantity.
So like, when you're going back, like in the amount of theorem, we're going from a function to it's the
Right,
derivative.
right.
When we're going back from the derivative to the function, how do we know if it's definite or indefinite?
In the mean value theorem.
Yes.
Okay, so the mean value theorem is not about the indefinite or indefinite, definite. The mean value theorem just relates a property of all continuous differentiable functions. All differentiable functions, whether that function is f, prime, or h. Okay, so that's why we can substitute there. You and I probably, our conversations would have to be a little bit longer, so why don't you come by, let's talk about that. Because you have class next week.
I am free, yeah.
You would- Yes, we'll see.
Can you just write it on the board?
Just take a picture of this and say, Ms. Yam says this is all you need. This speaks volumes.
Say hi to Sam.
Hi,
Nicola.
Nicola. Okay, come outside, Jabra.
Okay. Well, that's gonna get me older.
I'm actually free now.
So you are free now. Okay, yeah, we can. So your question's a little bit more involved than 1 second. I'm close.
So the actual C, right? And the
Yeah.
Yes, ma'am.